Okay, maybe I'll get started. Last class, we were talking about solutions, numerical solutions of some first order and second order differential equations. We use what's called the Euler method to solve numerically those equations last class. This class, I want to continue with numerical solutions of first order and second order differential equations. This time we're going to use what's called Runge-Kutta methods for solving these differential equations. Actually, the Euler method is the first order Runge-Kutta method, and the Runge-Kutta methods are really a big family of methods. We'll see that. So, as I mentioned, we looked at both first order on the left-hand side of this slide and second order differential equations in the last class. Upstairs here is a kind of general expression for a first order differential equation where the first order differential of some dependent variable can be some function of the dependent variable and the independent variable. And we looked at the example of a falling body under gravity and the first order differential equation for the velocity. And that gave rise to kind of polynomial solutions. In today's class, we're going to look at another type of first order differential equation. It's going to be of this form here, which gives rise to exponential solutions. So this is a form that is common in systems where you've got growth or systems where you've got decay, and it gives rise to the exponential function. Classic example, right, is the charging up or the discharging of a capacitor. So we're going to look at that type of differential equation as an example of first order differential equation. And then as we step over here on the right-hand side, upstairs here, I got the general form of a second order differential equation. So in that general form, the second order differential of some dependent variable is some function of the dependent variable, the first differential of the dependent variable, and the independent variable. So that's our general form. In the last class, the example we looked at was again that of a falling body, where the differential equation for the position of the falling body is given by a second order differential equation. So we went ahead and solved that. In today's class, we're going to look at another class of second order differential equations that come up a lot. A classic example here is, say, a mass on a spring, where there's a restoring force due to the spring. And here's this second order differential equation that describes that. And we're going to look at the solutions of that. So by looking at the differential equations from last class and today's class, we're really covering a broad spectrum of differential equations. We got from the last class, those with polynomial solutions. We've got from today's class, ones with exponential solutions and ones with sinusoidal solutions. And really, almost all the differential equations will meet are some sort of combination have some sort of combination of polynomial, exponential, and trigonometric solutions to them. So we're really trying to cover that whole kind of space of solutions to differential equations.